Let's talk about decomposition of a signal into fundamental signals. We will start with a simple decomposition and then move on to Fourier series decomposition. Let's consider the following example signal, which is a pulse train. As you can see, this signal is periodic with period 2, and between 0 and 1, its value is 1, and between 1 and 2, its value is 0, and then it repeats with period 2. Let's say we consider a single pulse as a fundamental signal and all its shifted versions shifted by 2 or multiples of 2 also as fundamental signals. And I want to express these signals as a sum of those signals. This is what it looks like, right? So here is our original signal, and which is a sequence of pulses. And I want to express this as a sum of all these signals, right? So this is the first pulse, this is the pulse shifted by 2, pulse shifted by 4, and so on. And as you can see, if you add all these 5 signals, you will get back the original signal. Let's call this first signal as x0 of t, and the signal shifted by 1 period as x1 of t, shifted by 2 periods x2 of t, and so on. Then mathematically, I can write x of t as sigma I equal to 0 to 4 xi of t. This sigma is nothing but x0 of t plus x1 of t, so on until x4 of t. We can also observe that all these xi's are related to each other, right? So for example, x1 of t will be x0 of t shifted by 2. Let's say our capital T, which is the fundamental period, is 2. Then x1 of t will be x0 of t minus t, x2 of t will be x0 of t minus 2 times t, and so on, right? So in general, xi of t will be equal to x0 of t minus it. This means that our original signal x of t, which was from I equal to 0 to 4 xi of t, we can replace each xi with x0 of t minus it. So if you look on the right hand side, all you need to know to completely compute the right hand side is just x0, right? And so we are representing x of t in terms of these fundamental signals as a sum of fundamental signals, and all the fundamental signals are also related to each other through the base fundamental signal. So what if xi of t was an infinite pulse train? So instead of just 5 samples like this, instead of 5 samples, what if we had infinite, right? This pulse train is going on to infinity in the positive and the negative time direction. In this case, instead of adding just 5 signals, we would have had to add infinite signals. And the mathematical expression in that case would be xi of t will be I equal to minus infinity to infinity x0 of t minus it. Note that for each I, we get a shifted pulse signal. And then therefore we have infinite I, so we have infinite different shifted pulse signal. And if you add them all up, you get your infinite pulse train. So what we are discussing here is a very simplistic decomposition of some periodic signal into its fundamental, in terms of fundamental signals, where we have a periodic signal and we are expressing this as a sum of shifted single periods, right? Now, okay, so let's look at, so before looking at a bit more sophisticated fundamental signals, let's look at an example where, can this be of use somewhere? Consider the example of pulse amplitude modulation. This is a very simple digital modulation technique. Let's say we want to transmit a sequence of 5 numbers. In this case, these numbers are 1, 4, 4, 2, and 4. So what we do is we take a pulse, and which is of certain period, and within each period we multiply that pulse with that number you want to transmit. In the next period, you multiply with this next number, and so on. So you get this sequence of different amplitude pulses. At the receiver, when they receive this signal, they can look at the amplitude of this pulse and say, okay, for 0 to 2, the amplitude is 1. So I will say that the first number was 1, the second number was 4, and so on. So this time, we can mathematically express this signal, x of t, as a sum of not just the shifted fundamental periods, but weighted and shifted, right? x0 is weighted by 1, x1 is weighted by 4, and so on. In sigma notation, then this expression looks as follows, where x of t is sigma equal to 0 to 4. we take the ith signal, which is just the fundamental, it's zero signal shifted by I times the fundamental period, and then you weight it by a certain coefficient. Okay, so these coefficients are basically these amplitudes. So what is the main takeaway from this discussion? First is we can express signals as weighted combinations of fundamental signals. For example, here, this signal, we express this as this weighted combination of these fundamental signals. Now, depending on the choice of these fundamental signals, the coefficients or these weights have specific meaning. So in this case, we chose our fundamental signals as these shifted pulse signals. If that was our choice, then these coefficients basically are telling us what is the amplitude. The ith coefficient is telling us the amplitude in the ith time interval, right? So if you choose a different set of fundamental signals, then those coefficients will mean something else. So that's the key takeaway. So now let's talk about Fourier series. So for Fourier series, we make a very specific choice of fundamental signals. Say we have a signal, in fact for any signal with fundamental period t or f0 equal to 1 over t. Note the difference here. So when we were talking about this example, the fundamental signals were these pulses, right? So the fundamental signal was very heavily dependent or very heavily dependent on what the original signal was, right? Because the fundamental signal and the original signal are the same within a given period. But now, when you're talking about Fourier series, we are talking about any signal with fundamental period t, okay? And our fundamental frequency f0 will be equal to 1 over t. And our ith signal is e to the j times 2 pi I times f0 t. That means if this is a complex exponential signal with I f0 as the frequency, right? And if you recall, e to the j theta is cosine theta plus j sine theta. This is called the Euler's identity. If you use that, you can write this complex exponential as a sum of two sinusoidal signals. Note that this is cosine plus j sine. And for each of these cosine and sine, the frequency is I times the fundamental frequency. So if I is 0, you get, this becomes 0, you get just a signal which is 1. If I is 1, you have the fundamental cosine plus the f0 sine. If I is 2, you have 2 times the frequency cosine, 2 times the fundamental frequency sine, and so on. So these are all our the signals which we will use to as our in place of these fundamental signals here. So now that we are using the word fundamental for fundamental frequency, I'm going to start using a different word to say all fundamental signals, and I'm going to say basis signals. So SI of t would be the ith basis signal, capital T would be the fundamental period, and F0 will be the fundamental frequency. And this will be our choice of basis signals. So given any signal which has a fundamental period t, we want to express it as a sum of weighted combinations of these signals. So mathematically, you can write it like this. So any given signal x of t, this has a fundamental period capital T. You want to write this as a sum of weighted combination of these basis signals. And if I substitute for SI of t, then I will get this particular expression. So this is called the Fourier series expansion of x of t, also sometimes referred to as Fourier series representation of x of t. Let's consider a simple example here. So x of t is 2 times e to the j 2 pi 1/3 times t plus 4 e to the j 2 pi 2/3 times t. So here the fundamental frequency is 1/3, and therefore x1, the first coefficient, is 2, and x2 is 4. Now that this 2 is the weight of the fundamental frequency signal, and 4 is the weight of 2 times the fundamental frequency signal. Okay, and that's how we get this. And then basically I want you to pause the video and compare these to that sigma notation there. This was a simple example where the signal itself is given as a weighted combination of your basis signals. So that is why we could directly read out what the coefficients were. What if the signal is not given like this? So let's consider a signal which looks, for example, the same pulse train, but slightly modified in the sense that the pulse is now centered at 0, and the fundamental period is still 2. So 0, 2 is the next center, minus 2 is the previous center, and so on. And the fundamental period is still 2. So let's say this is our signal. How do we determine what the Fourier series coefficients are in this case? So let's be a bit more specific here. So this signal x of t is specified like this, where x of t is the u of t plus half minus u of t minus half, where u is the unit step function. And x of t plus m times t is x of t for all m in the set of integers. So this basically means that the signal is periodic with period 2. And in this particular expression here specifies what the signal looks like within a single period. Okay, so this is our signal x of t, and we want to express this signal x of t as the summation here, where we want to express x of t as a weighted combination of these complex exponentials. So complex exponentials are our basis, and this should be I times f0. Okay, so we want to express x of t like this. So what should xi be equal to? It turns out xi of xi can be found by a formula given like this, like 1 over the fundamental period, an integral from minus t over 2 to t over 2. This integral limits can be in any period. So for example, it can also be from 0 to t, right? So as long as you're integrating over one period, that will be good enough. Times x of t times e to the minus. Notice the difference here. Here it is plus, here it is minus j2 pi f0t dt. Right? You can use this formula to find out these weights, which is very convenient, right? Now, there is a simple derivation. You can actually derive this. In fact, for Fourier series, this derivation is not very difficult, but we will table that derivation for later, right? So right now, what we want to know is, okay, given any signal, the fundamental period capital T, you want to express x of t as a weighted combination of these complex exponentials. Then what should these weights be? These weights are given with this, using this formula here. Now, if you take this expression for the signal x of t and then plug it in here, and you do some integration, you get xi is half of sinc half I, where we are adopting the definition of sinc x as sine pi x divided by pi x when x not equal to 0, and it is equal to 1 when x equal to 0. So using this expression, I'm going to substitute these xi's back in this expression here, and I'll get x of t. So basically my original signal x of t, I can represent this as the summation there, right? So then where these here are xi's, right? So these are the weights, and then there's a weighted combination of these complex exponentials, right? So unlike our example here, where it made like very obvious sense what this alpha I should be, over here it is not at all obvious why, if you add like these signals by weighting by these coefficients, you will get back this. It's not obvious at all, right? But that's what we get. Okay, so the best way to see this is using example and see what happens when we change I value here. Let's say that, if you put different limits and you compute the sum, what will the sum look like? We're going to use Matlab, and then we're going to use different values for the summation. So from minus k to k, and a half, the same thing here. And let's call this, let's say x hat of t, right? Because this is a finite sum, you'll never get back exactly equal to x of t. And what we have here is x of t is I equal to minus infinity infinity, this summation, okay? But we cannot compute minus infinity infinity, so we'll compute minus k to k and see what these sums look like. So this is a simple Matlab code that I wrote to demonstrate this. So this is our original signal, x of t. So this variable k here is controlling the k in this summation. Okay. So let's run this here, the script, and see how the reconstructed signal for k equal to 3 will look like, right? So I'm going to superimpose the reconstructed plot on this. So let's run this. So that the signal in the red is the summation, right? So Note that this is supposed to be infinite summation, but even just for I equal to minus 3 to 3, I get back almost the original signal. Well, there's a little of distortion, but it's not bad reconstruction. So now let's see what happens when I change k equal to 10. Okay, and let's run this. So again, now for k equal to 10, we get back even further the signal. Let's go all the way to 100 and see what happens. And now, the reconstructed signal is very close to the original signal, right? Note that these peaks here, this is like a very specific artifact of this particular example we have chosen. And these ripples happen because in this example, there is a discontinuity. It turns out Fourier series doesn't deal with discontinuities very well. But if the signal was like a very smoothly changing signal, you would have gotten back very close to what the original signal was. So let's come back to our discussion here. So previously, when we used our basis signals as the shifted pulses, these weighted coefficients, if you wanted to interpret these weighted coefficients, they were the amplitudes within each time period, right? So now we took a sample pulse train and we are expressing this as weighted summation of these complex exponentials. So the question is, what do these weights mean? Okay, so this is basically, these weights actually form the spectrum of the signal. Okay, and these weights tell us basically how the energy in the signal is distributed over different frequencies. Okay, so that's basically how you interpret these weights. And this particular interpretation, like if you want to find the spectrum of a signal, that particular finding the spectrum itself has lots of applications. Okay, and I don't want to go through a huge list of applications here. This video is primarily meant to show Fourier series. So that's basically how you interpret or what this summation is, right? This summation is nothing but you take a periodic signal and you want to express it as a weighted combination of these basis signals. Okay, and these basis signals are very specifically chosen as complex exponentials. And in general, if you want to compute these weights, sometimes it's easy to read it off the way x of t is given, but most of the times you have to use this formula to compute them. Okay, so that's about Fourier series.